Liftoff. 32 minutes past the hour. Liftoff.
The James Webb Space Telescope is located a million miles from Earth in an area of space with a name that sounds like something straight out of a science fiction novel. This piece of technology is said to alter our understanding of the cosmos and our place in it, because it is the largest and most powerful space-based telescope ever built. In today's video, we will be discussing the potential of the James Webb Space Telescope to uncover the deepest secrets of the universe. The James Webb Space Telescope was launched on December 25th by an Ariane 5 rocket from French Guiana and is marketed to be the successor to the famed Hubble Space Telescope. Its main objectives are to photograph the very earliest stars to shine in the universe and to study far-off planets to see if they are livable. Webb is outfitted with a 6.5-meter wide primary mirror to provide it with the resolution and sensitivity it needs to complete that mission. However, because this is an 18-segmented reflecting surface and it is so large, it had to be folded to fit inside Ariane's nose cone. The demand to unpack the mirror and other optics as well as get them all working in harmony has therefore dominated the initial activities since launch. Small motors have been used to alter the orientation and curvature of each of the 18 segments, allowing them to function as a single monolithic surface. We've now achieved what's known as diffraction-restricted alignment, in which the images are focused together as finely as the laws of the physics allow, said Marshall Perrin of the Space Telescope Science Institute in Baltimore, Maryland. The $10 billion James Webb Space Observatory, NASA's largest and most powerful space research telescope, will explore the cosmos to learn about the universe's history, from the Big Bang to the birth of alien planets and beyond. It is one of NASA's great observatories like the massive Hubble telescope that stares deep into the universe. The James Webb Space Telescope has traveled over 1 million miles, 1.5 million kilometers, to its permanent location, the Lagrange point, a gravitationally stable location in space, in 30 days. On January 24, 2022, the telescope reached L2, the second Lagrange point between the Sun and Earth. L2 is a point in space near Earth that is opposite the Sun. This orbit will keep the telescope aligned with Earth as it orbits the Sun. Other space telescopes such as the HERSCHEL Space Telescope and the Planck Space Observatory have used it as a launch pad. To understand how far the James Webb Telescope can travel back in time, we have to consider the following scenario. The speed of light is around 300,000 kilometers per second, or 186,000 miles per second. Light from the Sun travels to us here on Earth in about 8 minutes at this pace. On a sunny day, the rays are 8 minutes old, implying that we are not viewing the Sun in real time, but rather an 8-minute-old sun. Now apply that same logic to additional stars visible in the night sky. Most stars are light years apart, as you may know. A light year is 9.46 trillion kilometers, or the distance that light travels in a year, 5.88 trillion miles. Proxima Centauri, the nearest star, is 4.2465 light years away. Therefore, the light from this star is only a few years old. The JWST telescope will investigate several stars that are tens of millions of light years away. We would probably be able to observe dinosaurs through a telescope if we were to stand on a star 65 million light years away and then look towards Earth. The JWST has a mirror that is substantially larger than any other space telescope. A telescope's mirror size determines how much light it can capture. The main mirror is 6.5 meters or 21.3 feet in diameter and is made up of 18 smaller hexagonal mirrors. Each little mirror is covered with a very thin layer of gold, which is the best metal for reflecting infrared light. Because of the JWST's improved sensitivity and configuration, the mirror will be able to pick up longer wavelengths from further back in time. Infrared radiation is only a form of electromagnetic radiation with a longer wavelength than visible light, even though it does sound lethal. Consider the sun's light as a wave that travels to the Earth. Stretch it out even further. Although our eyes are not designed to sense infrared radiation, we are exposed to it and use it every day. Infrared radiation is used to control your television, for example, through your TV remote. The Earth also radiates heat in the infrared spectrum, which we can feel. Because of the effect of the universe's expansion on light traveling from hundreds of light years away, the JWST was designed as an infrared telescope. Astronomers will investigate the light emitted by the first stars and galaxies with this telescope. However, because this light has traveled a long way to reach the JWST, it will have been stretched from visible light to a longer wavelength of infrared radiation by the expanding universe. This is referred to as redshifting. The JWST will also look for exoplanets that may have the capacity to support life, but we won't be able to see through their hazy atmospheres with visible light. Because of its longer wavelength, infrared radiation can break through the interference and produce a more detailed image of interior nebulas, dust clouds, and other objects. Because the JWST is seeking infrared radiation, any incoming light or heat from other stars or heated objects could interfere with its images. NASA engineers devised a 5-layered sunshield to keep the mirror and equipment at a freezing -220 degrees Celsius. It's the ideal weather for a trip into space to gaze at the stars. There were no planets known other than those in our solar system when the earliest plans for JWST were proposed more than 20 years ago. Thousands of planets orbiting other stars in our galaxy have been discovered since then. According to astronomers, exoplanets. The study of their atmospheres will take up a large portion of the JWST observing program. JWST's wavelength coverage is especially well suited to analyzing chemicals in extraterrestrial atmospheres, as well as the low infrared background radiation from space, giving it a significant edge over Earth-based observatories. There are two methods available. One takes advantage of the fact that planets can transit in front of their parent star, causing a dip in the light that we perceive from it, called a transit. We may explore the planet's atmosphere to discover what molecules it consists of by analyzing light broken down by wavelength with remarkable precision before and during transit. Another method involves blocking the light from the parent star with a piece of special equipment called a coronagraph, which allows direct imaging of the planet and research of its atmosphere or surface. This could reveal whether a planet is habitable, necessitating further inquiry, and perhaps the deployment of small space probes in the future. JWST will be able to observe our planetary system in addition to investigating planets outside of our solar system. Its high sensitivity will allow it to identify and characterize comets as well as other things in space made of ice. These things have remained virtually intact since their birth in very remote regions, and they may offer clues about Earth's beginnings, particularly about the source of its water, which could be the result of bombardment by such bodies early in its lifespan. The expenditure of developing an ambitious, game-changing telescope has to be justified with detailed plans and concepts for what will be discovered. In the comments area below, tell us what you think about the latest and possibly greatest space development. Remember to leave a like and subscribe to this channel for more interesting videos like this. Turn on your post notifications and stay tuned so you don't miss any updates from us. Until next time, stay safe, people.